Welcome to today's Deep Dive Explainer. We are jumping right into one of the absolute most destructive and honestly terrifying faults you can encounter in an electric vehicle's high-voltage system. We're talking about high-voltage contactor welding, or what we map out as the P0AA1 and P0A2A fault codes within the system high-voltage execution and global safety layer. It sounds highly technical, I know, but the physics behind this failure and the extreme engineering required to prevent it are just completely mind-blowing.
Picture this extremely high-stakes scenario. You park your EV, hit the power button to shut it down, and the screen goes black just like normal. But right under your feet, the battery pack is still fully active and live. The car has literally lost its physical ability to cut off high-voltage power. Those physical switches, the contactors, are jammed permanently shut, leaving massive amounts of energy totally exposed. That is the very real, very dangerous reality of a P0AA1 or P0A2A fault.
Because this exposed high voltage is just incredibly dangerous, especially after you shut the car off or during an emergency. This specific fault is slapped with the absolute highest functional safety and severity rating in automotive engineering, ASIL-D. In the engineering world, ASIL-D means there is zero margin for error. The fail-safe mechanisms have to be absolutely bulletproof.
So how do engineers systematically conquer this ASIL-D level problem? Well, we've got a 5-part roadmap today. 1, root cause analysis. 2, hardware and software co-diagnostics. 3, DFMEA design prevention. 4, PFMEA process control. And 5, DVP&R validation. Let's dive right in.
Dimension 1, root cause analysis. This is essentially our crime scene. The absolute main culprit here is something called metallurgical bonding. You see, when an EV tries to cut off massive, highly inductive direct current, it doesn't just quietly click off. In the microsecond the contacts pull apart, the current jumps the gap, pulling a high-voltage DC arc that burns at thousands of degrees. This extreme heat instantly melts the silver tungsten or silver tin oxide alloy on the contacts. Fractions of a second later, that molten metal rapidly cools, irreversibly welding the moving and static contacts perfectly together. The switch is permanently locked. So what exactly triggers these 1,000-degree arcs? It boils down to a rule of 3. First, pre-charge timing failures. If the system tries to close the main contactor before the voltages match, the extreme voltage difference creates a massive inrush current that instantly melts the contacts. Second is hot switching, which is forcing the load off while the car is pulling huge amounts of current, blowing right past the material's arc tolerance limits. And third is assembly torque deviation. If a bolt is even slightly loose, contact resistance goes up, generating localized Joule heating. That heat slowly fatigues the internal springs until they just don't have the physical force to snap the switch open anymore. Moving right into Dimension 2, hardware and software co-diagnostics. These are our shields. Since physics is kind of working against us here, how does the battery management system, the BMS, detect this disaster in mere milliseconds? It uses a brilliant two-pronged approach. On one side, we have the pure hardware defense, the auxiliary feedback check. There's a tiny low-voltage pin physically linked to the main high-voltage switch. If the BMS says, open, but that pin reports, hey, I'm still closed, we instantly know we've got a physical weld. On the software side, we use dynamic voltage timing diagnosis. When you shut the car down, the BMS watches how fast the inverter's busbar voltage decays. If it stubbornly stays above 60 volts instead of dropping, the software completely confirms the hardware's worst fear. The really critical part is what happens next. The second a weld is confirmed, the system triggers an immediate failsafe. It writes a permanent diagnostic trouble code, completely locking down the state machine. It permanently forbids the car from entering the ready state to drive, and it completely blocks any AC or DC charging requests. It's a total, rigid lockout until a technician physically replaces the fused relay module. But what if this metallurgical bonding happens during a catastrophic event, like an extreme collision with a massive overcurrent surging through the system? A standard relay is totally useless here. That's when the ultimate failsafe kicks in. The restraints control module, the exact same system that deploys your airbags, fires a hardwired crash flag straight to the BMS. The BMS bypasses all software delays and sends an instant ignition pulse to the Pyro-fuse. This is literally an explosive device built into the high-voltage line that physically detonates the circuit to kill the current and snuff out the arc. Shifting gears to Dimension 3, DFMEA, Design Prevention. This is the armor. In the Design FMEA, this specific fault earns a severity rating of 9 out of 10. That means there is zero room for error, which proves exactly why the engineering controls we're about to look at have to be absolutely flawless before a single car is ever built. To prevent this from ever happening, engineers bring in the heavy armor.
First, they fill the arc chambers with nitrogen and use powerful magnets to create a Lorentz force, which physically stretches and snaps that DC arc in a fraction of a second. Next is zero current switching, where the software strictly forces the current under 1 amp before it even allows the contactor to release. Then there's the pre-charge voltage check. If the bus bar voltage doesn't hit 95% within just 300 milliseconds, it completely rejects the closure. Finally, Belleville washers. These are special conical springs that compensate for thermal expansion, maintaining massive clamp force so those bolts never loosen up from thermal fatigue.
That brings us to Dimension 4, PFMEA, process control, taking it straight to the assembly line. How do we guarantee these precise designs are built flawlessly at scale? It all comes down to incredibly aggressive manufacturing controls. We're talking 100% servo smart tightening on the bolts and 100% incoming quality checks for initial contact resistance. Because these relays have sensitive magnetic damping, they have to be handled in strict anti-drop precision trees. Drop it once, and the internal magnets get misaligned. Finally, every single unit goes through a 100% end-of-line timing and dynamic welding check before it ever leaves the factory. Those smart tightening tools I just mentioned, they use a highly precise torque angle dual dynamic judgment process. They measure the rotational force and the exact angle simultaneously, guaranteeing massive clamp force without shearing the threads. Every single data point is captured and tied to the battery pack's barcode, completely eliminating human error and stopping that dangerous joule heating right at the source. So the theoretical design is perfect, and the manufacturing is locked down. But that leaves one ultimate question. How do we actually prove this entire safety architecture works before giving the green light for mass production? We can't just hope for the best. Welcome to the fifth and final dimension, DVP&R validation. This is the ultimate proving ground. Here is where engineers intentionally try to destroy these components. In the hot switching endurance test, contactors are baked at 85 degrees Celsius and forced to cut 400 amp loads over thousands of cycles. For the pre-charge inhibit test, they use hardware-in-the-loop rigs to deliberately inject a broken resistor fault, creating a dangerous 5% voltage variance to make sure the software intercepts it. And for assembly stress, they literally bolt the terminals down at 150% over torque and 50% under torque just to prove the electrical pathways survive extreme physical abuse. Remember that pyro-fuse for collision scenarios? During validation, they force a massive short circuit, trigger the crash signal, and grade the system against an impossibly strict metric, less than or equal to 2 milliseconds. The system must recognize the crash, send the pulse, and physically explode the circuit in 0.02 of a second to prevent thermal runaway. After surviving all of that absolute torture, thousands of hot switches, extreme heat, and injected faults, there's one final passing criteria. The dynamic contact resistance of the main contacts must remain strictly under 0.05 milliohms. The auxiliary contacts can't stick, and there can be zero signs of macroscopic melting on that silver alloy. Only the contactors that pass these microscopic standards after extreme abuse are finally approved for the road. And that wraps up our anatomy of a disaster prevented. We've completely secured the main contactor against metallurgical bonding. But this naturally leads to a really provocative question. With the main contactor totally locked down, how do we verify the next layer of crash safety, the high-voltage interlock circuit, during an extreme collision? Well, you'll just have to stick around for our next explainer to find out. Thanks for joining us today, and keep exploring the incredible engineering all around us.